Maybe hard to tell, but the lab is full with a lot of noisemakers here. So that's why you see me moving at the back here. But I'm gonna get started real soon. I hope everyone is doing okay. I thought that I would do, wow, Enzo is here to hear me criticize his paper, but I'm
Hello.
gonna go ahead and present it, and we will, uh, yeah, we'll get started. I think this is it. So the reason why I chose uh, this paper is one, we're hosting the datathon, as you can tell from the background, and it's gonna be awesome. A lot of the faces here are coming, and I thought that this is a good reflection of what needs to be done, and I think it's a good way to do this. So this is part. Oof, I need to silence the choo-choo. Wait 1 second, because that kind of annoys me. No, we're not hot, Dr. Newsom. Stop ruining our lab space. So this paper talks about do you guys need a link or you're fine? So this paper talks about open challenges on fairness of AI in medical imaging applications. And, I think that it's an important thing for us to think about writing this type of things. Now, it's part of a book, and I was impressed that Enzo, who will actually be one of our summer school and datathon guests, to decided to publish this on archive. As you know, most of the time the book stays on, and so I think it's a good time, I think, to provide feedback and think about it. So this is a paper that discusses what are the open topics and looking from metrics, how to audit, what is called the leveling down effect, task difficulty, which is a topic that I'm very, very interested in, and then discovering biases in a known population, and then explaining biases beyond as social, standard demographic attributes. This remains some of the biggest challenges for us to solve for medical AI imaging. And one of the best things is that we've seen quite a lot. When you would see this in the US, you'd see that some people felt, oh, this type of job should be done of research should be done by a specific group of people. But I think it's very clear that there's quite a lot of appetite for tackling, you know, issues around bias and fairness from even more what would be considered as more serious researchers, because there's quite a lot of methodological approaches that need to be developed. So the paper starts off with, talking about the issue of fairness and that bias can exist not just in medical imaging, but face recognition, loan allocation, healthcare data. So this paper should be familiar to most people on this group, and, sets this as a grand challenge work that needs to be done. And so it's the section 1.3 looks at common pitfalls when you audit with bias metrics, and then section 1.4 looks at leveling down effect that appears to be a common consequence of bias mitigation strategies, and then 1.5 looks at task difficulty, and then 1.6 looks at bias in unseen populations, and then 1.7 looks at beyond demographic attributes. So, as usual, most of us will agree that bias is divided into data, models, and people. And this is an area that our group has really been thinking about a lot. We spent pretty much the first half of this year trying to narrow down, like, when do you say a model is biased? And as recent as one of our summer students, when I was presenting 2 weeks ago, especially when we use foundation models, it even brings another complexity, because this is not just a model, it's a model as a data set. And because the foundation model, and there has been many, many pieces of work actually done by quite a lot of people on this call, or who are working on them, that shows with the foundation model, you do have a problem that can occur because the data that was used to train the foundation model could have bias itself, and then the downstream model. So you're starting with a generalist model. So let me step back. Now, when you think about like the ChatGPT equivalent, right? So we're seeing those type of foundation models being built in medical imaging. Now, I would say that there are kind of two forms. There's one that is trained on all images, and then you just have the model that you fine tune. But then there's also this other form that you get, which is more of just the embeddings. They extract the features and then you fine tune the embeddings. And for those people who attended the Datathon last year, this was there, and this year we will. This work, most of the work has been done by the Google team, and I do hope that they will be showing up this year and we'll be discussing this. And so now when you bring the concept of model as a data set, in the current pipeline, you input your test X-rays, then you change your layers and your hyperparameters, and then you finally have your prediction. But when you have a foundation model that, let's say, I got from Dr. Newsom, and now I'm using it to train a pneumothorax or pneumonia model, I may not have visibility to that model. And I think most of the work, I mean, Ben Glocker showed that this can also, they do encode some of the biases, but we also, I think our journal club discussion finally decided that we didn't know enough around should you attribute that the bias is because of the foundation model, or, and I'm looking around because all my students are behind me, or or should you attribute this because of the downstream task? And so it's almost like you have now to debias the foundation model and then the downstream task that you have. So I think most of the time, and this is a question I'm going to pose to the people on the call, is you have to think, when is a model just a model bias, and how do you frame that? And you can use the chat, or you can wait when I'm done, you can sort of react to that. We do know for people, it's pretty clear, especially with the automation bias and the new things that we are finding with the human factors engineering, and data set bias is also pretty well described. But this is trying to get this mental picture of where the biases come. One of the papers to look at this is the Midrick paper that shows sort of like that intersection of bias across multiple things. I think I have a talk that I give today that should have this. And so it's this type of like we've always thought of it as data bias, model evaluation, and model deployment. So what would be some of the things that we think are truly just because of the model? And this is a big debate also, because the computer scientists think, everyone always says, but it's the data set that is biased. But for a long time, in this era now, we can think about models as data sets. So, the section 1.21 starts off with data. And we know that data imbalance is a common problem. It's not only just the occurrence of disease, where you find that many of the studies can be normal, but it's the percentage of abnormality in an image. We see this especially for mammogram images, where we can have a mammogram. Those are pictures of the breast, and the abnormalities like there, right? So it's less than it's even less than 1% of the image itself. And so this is very challenging, especially if you think about the model things that we do, dropout, scaling, the size of the, of the resolution, and what those mean for downstream impact for model prediction and fairness. And we will be discussing some of our lessons this way for the people who will be able to attend the summer school, because we've been thinking a little bit about this. And so how you deal with class imbalance is important, because if some people upsample the minority class, other people downsample, but we also don't understand the impact of these changes in the dataset distribution that you're doing in terms of the class balance on the downstream task, which has a different distribution from your original task. And so and also I think work from Mazia showed that differential privacy, which tries to minimize the class that you can easily identify, which tends to be the minority or the rare disease, then can also be harmful for health equity, because now you're even further affecting the minority subgroup. And so, biases can, the authors write here that the biases can also be encountered due to differences in the properties of the imaging data between protected groups, or to spurious correlations for shortcut learning. This is definitely something that Judy remains interested in. So this is again, trying to create that mental model of data, people and models. And you have to be thinking, and so this first chapter is saying like, why is my system biased, right? What should you be thinking around as you move on, is that you have to be saying, if multiple pathologies are present in a data set, are there enough examples of each pathology for each subgroup? And intersectionality in terms of protected attributes should also be taken into account. For example, how does the fraction of Black females with condition A in the data set compare to white males with the same condition? And so, because if you have these differences in the data set, you can have a spurious correlation and shortcut learning, and that degrades the model for underrepresented subgroups. The way we've been dealing with this is to come up with a label correlation map. And this is super important, because if you say, I'm going to merge CheckSpot to the Emory data set, you have to see the similarity. And the work that I would say everyone should read this work is by the COVID work, which shows like sort of how we compose data sets and their impact. This work by Alex de Greve and Sanli. And so in this work, what they do is two data sets, right? This is COVID time. We didn't have COVID negative data sets. So you pick the chest X-ray 14, and then these two data sets. And that, you say part just, I believe it's a more pediatric one. So you have a positive and negative data set, and you build an AI model to predict COVID, and you see the internal performance is pretty good, 0.99. But then when you do the external performance, you see external validation, which are these models, that the performance degrades quite a bit. And it's converse, right? When they test both data sets. But then when you change the last layer of the model and you say predict something different, like patient sex, you see that there's no degradation of the patient sex in this model, where you almost have perfect performance irrespective, and very different from the original data set. So two things to think about this when you think about model is clearly how we compose the data sets, and how much should we artificially inflate this. Enzo did the work for sort of sex imbalance and the impact. And most of the time when you talk to people, they want to hear a solution that says, look, you should be creating a data set that has 50-50 Black, white, male, female, or something like that. But it turns that we don't know the exact subgroup composition. And the other thing that you have to think about here is the label correlation. So for the clinical people, if you have pneumonia and atelectasis, in terms of visual appearance, maybe the distribution may be different, but those are just white, and so those two may tend to be correlated. If you have a pleural effusion, then you're squeezing the lung, so it most likely is correlated with, atelectasis. So, and here says, you should be thinking beyond binary disease labels, right? So whether there's pneumothorax, non-pneumothorax, and you should be incorporating more detailed information into the analysis. And then you should be even more cautious when you see an equivalent or higher performance for underrepresented groups, because the same concept of shortcut learning, maybe, for example, the situation is flipped when I go back home in Kenya, where most of the studies are abnormal, and while in the US, most studies are normal. And so that can affect the model performance. So these issues around data quality, differences in equipment and imaging, I can tell you that from our datathon last year, this was a big lesson for us. Now we keep our data set in the DICOM format. We've learned a lot about preprocessing about that. And the reason why this is important is because when you convert to the PNG or whatever format that you do, you lose a lot of metadata and you cannot go back and reprocess the data set that way. Now, it's more difficult to anonymize, but this is a real problem. And as you know, most of the time, we don't really like you never even have the medical imaging equipment in terms of the metadata that are available in a data set. And if you remember, Professor Poti, who's actually in the room and visiting us, discussed just predicting race from the metadata of the chest x-ray, showing that you still can do that. And so finally, it's not, data balance is not at the configuration of the data set, but you have to think about this throughout the development of the model. One of our students, Joao, did this work where you show sort of like every time you drop a subgroup, you end up showing what's the composition of the data set that's remaining. I'll try and pull that up and just show you it's a package now. And that's important to be showing how is your composition of your data set changing in the whole life cycle. And so differences in the data composition between the training and validation stands, for instance, may bias the model if early stopping is used to prevent overfitting. And when you lack batch stratification, you may have strong fluctuations in the representation of the protected groups within the batch, resulting in less stable learning for these groups. And I'll tell you, most of the data sets are just one, and I'd have to go back and see if most of like the leaderboard for CheckSpot usually have this type of granular, and if anyone knows, that's why we're in a crowd here, this type of granular thought process in terms of the labels themselves and what that, most of us will do the stratified split, maybe best if you're trying to predict pneumothorax, non-pneumothorax, and if you don't have enough cases, you'll bring them a lot, if you're not using the whole data set. But when you do this multi-class predictive problems, I guess I haven't seen what people are doing in practice and in terms of just thinking about splitting your test set. So when it comes to models, the choice of model class, complexity, regularization, and training strategy will result in different biases. I can tell you that really this is usually you either like a certain model in your group, or you look at a paper and it says DenseNet is the best model, or you come up and say you have to start random. And that's really the reality of our field, and so here, I think what they call out is mainly around calibration problems and, and uncertainty, which is a really powerful growing field. And so it's important, it's very difficult to know when and how the models will fail when confronted with novel data. And so, when they call out here that we are in an era of multimodal models, and so we are merging many, many features. And so sometimes how you merge and what you determine to be important features, I think can have an impact, and especially on, sort of like which are the more important features. And you think about this, like if you have 400 features, you have to choose, and those feature selection criteria can have a big impact on sort of your bias and fairness. But, I think one thing, Enzo, really that is missing, I'm not trying to criticize your work, is the work by Andrew King, which shows that even like the segmentation models, I would say that that's a good example showing it's not just data set, the segmentation models usually have different performance. And this is like a very robust task. This is this paper, an investigation to the impact of deep learning model on choice on sex and race bias in cardiac MR segmentation. It's not that any radiologist is looking at this and deciding, oh, this is for a female, I'm not going to draw it well. And so we see that this model performs different for males, females, and white Black patients, with underperformance for females and for Black patients in a segmentation task, which is, I think, a little bizarre, but maybe a good example of, of a model bias. So when it comes to people, right? So, the authors team look at not only those people who are collecting the data, model development, and funnel deployment, right? So it's the whole pipeline. This is why we do datathons, right? We want to improve more participation from a group of people and create a village of knowledge. And I think sometimes, and there's this example that is not medical, but is given like a decade ago, Google's photo app, right? So this was work by really spearheaded by Timnit. By the way, Timnit was a very, very instrumental in Judy's getting into machine learning, a very fantastic peer mentor. Um, opened a lot of doors for me. And so Timnit is one of the researchers at Google who were fired, and shows, calls out this how the Google Photo app identified Black individuals as gorillas, and say that maybe if there's diversity in terms of the developers, then people can pick up this type of things. There have been examples like using nail polish. If you don't have a female workforce, you may not realize that your device is not working for that subset of the population. And so, and say, look, only 2.5% of the Google's workforce was Black in 2019, with 4% in Facebook and Microsoft. And and also a caution, it's not that the problem is easy to solve or that diversity by itself is a universal fix of biases. But if you look at this 8 years after Google prevented its software from categorizing any image as gorillas, an investigative app by the New York Times revealed neither the Google's photo app nor Apple's can find gorillas, which is the real, thing that you wanted to find in the first place. So, a lot of work. I think other things from the people perspective that you should be aware of is really, I think we're missing from this work is around automation bias, which I think is going to be a big problem as we deploy AI systems. So this was, how do you figure out your model is biased, right? So you think about the people, the data, and the model itself. And, it's not just why, it's also where is my system biased, right? So you're a detective. I think one thing that is also missing in this grand challenge is how to think about, is my commercial model or is my FDA approved model biased, right? How do we think, because that's like a double black box. You don't have the model, you don't have the data that was used to train, but those models are still biased. And how do you think about auditing something like that? I think still remains a grand challenge. So the next section goes to bias metrics may result in misleading fairness audits. So the dice coefficient is like that example I showed you of the cardiac MRI, where you draw, you draw a circle, and you see that this metric is known to penalize missed pixels in small structures more than bigger structures. So it may be biased with respect to the size of the structure of interest, as it tends to be lower in smaller objects. I honestly did not know that, so that was good lesson for me. And so if you have, for example, a small organ or a younger patient, just different sizes where an organ can vary, or post-surgical changes in an organ, then you could get into trouble as you think about these metrics. And so in these cases, so adopting unbiased estimates of segmentation, like the normalized dice coefficient, could potentially help to solve this issue. And then another one is like the strong differences in image resolution, right? So I kind of drew that picture of a mammogram, and you can see that sometimes the hospitals, now this is a pretty sensitive issue because the newer equipment tend to have more higher resolution. And in medical imaging, you also have to think about film versus non-film imaging. And so if you use, for example, back in my village, they would have lower resolution imaging. So it's just like generation of your iPhone or Android phone. And if your aim is to audit an anatomical segment system, which is with respect to the geographic location, then this is a proxy for image resolution. And so you may observe a systematically lower dice coefficient for images with lower resolution than those with higher resolution. And so, and since you have that bias of the dice coefficient, then the bias may imply that systematically lower values for low resolution images. And so you cannot tell these differences in the dice gap, whether it's because of the metric bias or it's because there's lower segmentation quality for one population versus another. And so Now, if the prevalence of a condition varies from low, so for example, back home, most of the tests x-rays are going to be because of tuberculosis, then you could now have a problem, because then, the low resolution, this is just the ICU pneumonia prediction shortcut learning, right? So it learns to associate, oh, these low images, they tend to have TB, and I'm going to predict TB. And so this remains a big challenge, I think, in terms of thinking about shortcut learning and spurious correlations, how they result in bias. So that was for segmentation. I think this was good because this is not something that we discussed. This was new information for me. And then in the context of image classification, I think what we miss is model calibration. I've been involved in several papers from the ICU, just looking at model calibration, right? So you need more newer metrics that are actually also linked to the outcome. So calibration measures the reliability of the prediction probabilities. So a well-calibrated model produces probabilities that accurately reflect the true likelihood of outcomes. So while we see good performance, most of the models for deep learning have poor calibration errors. And so like you need quantifying this uncertainty for interpretability of outputs. And I'm not going to go down the rabbit hole of are interpretable models more fair, something like that. But if you have miscalibrated models, then you could have high error rates. And so, for example, if you use the expected calibration error, this is a metric that is very biased in respect to the sample size, and becoming worse when there are fewer sample size in the evaluation set. And so you have to be thinking how this varies. I have to say it in a different way. This has been something that I've been thinking about. Does bias, if you had the all the images in the world, would you ever finally have a fair model, not just in the terms of diversity of the images that are in there, but because the size is so large that the model lands. And I can tell you work done by Badia, one of our students, that is being written up, is that some of the tasks are very forgiving for even label noise, that the model will still learn the right thing, even if you have bad quality labels. And so I wonder, does size matter? And at what point does that size, matter? So alongside with the sort of the performance, there's this leveling down effect, where is that you're just chasing down the and something important around this work is the recent work we published with Mazia, which is the like the demographic limits of AI in the world. This one now, it's on Nature Medicine, that shows that if the models, right? So this is a paper that just requires a whole day to the session to discuss again. But essentially, we look at several data sets and look at their degree of encoding demographic attributes, including sex, age, race, and sex and race. And then we look at performance and fairness, and look at what's the difference in terms of demographic encoding and the impact on overall performance and fairness gap. And the models that encode race the most have the worst fairness gaps. So it's not just, it's a complexity of these metrics, and showing you again, like if we go back here, that when you think about calibration, and as you keep more removing some of the fairness metrics, you see some of the applying some of the debiasing approaches, you see changes in some of the other metrics, not just in performance and calibration. And so this leveling down effect occurs when fairness is achieved at the expense of making every group worse off, or bringing down better performing groups to the lower performing one. So for example, you could say the male model is performing better, but to make everyone fair, we're going to make males come down and raise females, right? So which is also like a little bit of the health equity picture that most people use. And so um they say that this is a little futile if you're just chasing the fair metric, because if you keep let's say you have a binary class which performs better in group A than in group B. If you keep replacing a fraction of the predictions by a coin toss will reduce the gap, but then you'll end up with a useless model. So one of our recent lab meetings, we discussed this fairness utility trade-off, right? So, but what we didn't understand, this was Zhao Li, who unfortunately is not able to come for the datathon, but has been doing this fairness metrics in terms of the vision language models. And, we wondered, like, what threshold do you need to be fair, and when do you decide the model, the utility of the model, who decides it, right? And so I think that's like my thought process around the leveling down effect. And, you know, and Enzo's teams say that if you don't have a useful model, then you're breaking the principles of bioethics, which one is non-maleficence, that you still have to have benefit. And so, for example, and also this has society impact, right? So people don't want their performance to go down, right? It brings a bad taste when you say you're working in fairness, because people think that you're trying to, now let's leave medicine, but loans, right? It feels like you want to take away from someone who has more money so that you can give someone who doesn't. And so that's why this tension can occur. And so to overcome this limitation is, first of all, to be aware of this issue and avoid reporting and analyzing only performance gaps or worst group accuracy. And we have to be looking at average and subgroup performance for both advantaged and disadvantaged groups. And so while you keep working on the algorithmic and model level biases using different mitigation strategies, this may not always be effective because there's strong differences in task difficulty. This is a super important fact. And so, one, this again is like the encoding the protected attributes, and an active line of research is to deal with these biases for demographical invariant representation, which are used for downstream tasks. I think the paper that Maze published talks about this, I think, best. And so this is just a caution about the general purpose trained embeddings, which is the concept I tried to explain around vision language models, like this model as a data set and then a downstream task, and what the importance of that is. So this concept of is a task just biased or more difficult, I think remains a grand challenge for us to figure out in computer vision. If you train a model and say, this is a dog, and you tell the species, and you give another model and say, it's never seen that species, the AI model almost says this is a dog with good accuracy, but it doesn't turn out that way in medical imaging. And so, for example, we know that there are some things, for example, if you have on a female chest X-ray, lung opacity can be, just obscured because of the female breast, right? And also like anything in the lung bases, or there's this earlier on, I would say, and I have also been at fault at this, saying that we should have a model, for example, just to train for Black or women. You should not do that. Those models don't work. They actually work worse. And so there's no right data set composition in terms of saying you need this number of females and males, but definitely you training a uni population model is definitely worse. And so we know that there are some tasks. One thing you have to be careful with this is that demographic attributes of interest like race correlate with breast density. Just be careful with this, because race is a social construct. We do see some types of breast density in specific subgroups of patients. And, if you see, for example, the way we've looked at this is to try and say, is pneumothorax an easy task? And then if you understand the work that was done by Lauren, Ogden Reyna, is that there's hidden stratification. So not all pneumothorax are the same. There's a large pneumothorax, there's a pneumothorax with a chest tube, there's a right pneumothorax, there's bilateral pneumothorax, there's a pneumothorax at the apex, there's a pneumothorax at the base. And you have to figure out which is a hard task for those. So how we're approaching it this year is to use transformer networks from two of our teams here to say, could we learn some of these characteristics in the auxiliary label? And then we can figure out, I think the transformer architectures are allowing us to start to figure out, do we still see the same type of behaviors and in terms of these data sets? And so this I think we see again here the recent work suggests that gender-based performance discrepancies in chest X-rays, especially in the NIH and expert data sets, are due to data set-specific factors rather than inherent physiologic difference, which we have to be careful about. And so it's not that the biologic the analysis indicates that biologic differences may not be the main driver of the male-female performance groups, and it's other things, for example, prevalence of label errors or recording quality or other confounders. So discovering biases in unseen population, I think, is very relevant, especially when you see a homogeneous population, or you're in Europe where social risk scoring, aka collecting data on like race, is prohibited. And so, and the team here start to say that if a system is fair, given a source population, when faced with a different target population, then fairness properties may not hold anymore. This is a big issue, especially as we've moved on to these centers of excellence that are coming up to say we want to credential models that are fair and give you a certificate, because it's very difficult to do. And just because I make the model fair and MRE, if I bring it to you, it doesn't mean that those fairness are going to be guaranteed. And so we know that there are demographic shifts across locations, across different race groups and other demographic factors. And this may end up decreasing the predictive performance or on a particular demographic group, and this may be outlooked. And so in this paper 38, I haven't unfortunately had enough time to read it, is there's a reverse classification accuracy framework. This was the first time I'd had this to estimate performance gaps between demographic groups. And so RCA suggests building a reverse classifier that employs a single test image along with its predicted segmentation as a substitute for the actual ground truth. And then following this, the classifier is evaluated against a reference data set that includes existing segmentation. So the performance is then utilized as an indirect measure of the predicted segmentation quality. I'm unfortunately unable to explain that further because I haven't read that paper. And so there are some methods actually that have been tried to use for that bias in unseen population. I think this is a place where embeddings can be a really powerful tool to figure out clusters of patients. In our own work, we've tried to really come back to false positives. Which patients or cohorts does the model not work well on? And then going back to investigate those further. And I can tell you that this has influenced how we are relabeling our data sets, actually, for the datathon. I think this was really a discussion with Jack that led to that downstream. I don't know how good it's going to end up, but one of the papers that we wrote was saying, we saw the AI model wasn't working well for Black women, but we also saw that if you increase the number of Black women, the model became narrower in fairness gaps, but the biggest fairness gap narrowing came from adding dense breasts. So if you look at biologic or clinical characteristics or something else that the model works better on, then those models tend to work better instead of just saying, I'm going to add more females or I'm just going to add something else. And so, there are some also mathematical ways that have come up in trying to think about bias in unseen populations. And just remember that example that I showed you, that the last layer can still encode a characteristic that you didn't provide. So finally, here on the home stretch, is that we have to think about beyond demographic attributes. This has been something that has been really on top of mind. Actually, for the symposium this year, we're going to have what's another label beyond just Black or white or male or female. And it's important to think about this because, if you for example, a lot of the work for pulse oximetry, I said it's not just black or white, it's, a skin tone differences, right? There's, for example, breast density, BMI, hospitalization conditions. Our data sets for medical imaging don't have this. And what we're seeing a lot of is someone says, I'm going to build a radiomics model and a pathomics model. I'm going to combine those and say, look, I'm finding new subpopulations that are not affected by prostate cancer or endometrial cancer or breast cancer. But the way that those groups are, they're not really using a discovery of just clustering to tell you what the data is telling you. They still come back to male, female. Those are reasonable, and also black, white. But the problem is you now start to go back to decades of really harmful research that was trying to say that there's a different biologic differences between different risk groups. And I think we need to think a little more about what's the opportunity, how should we be thinking about the data set, and what's the cost, because the more diverse your data set is, the higher the risk of re-identification, or at least figuring out who those patients are, what's the cost benefit ratio that is necessary. And so, there is this adversarial reweighted learning strategy, and this is a game between a learner and an adversary, where the learner optimizes the classification task. The adversary learns to identify regions where the learner makes significant errors, and this can be upweighted in the loss function, forcing the learner to improve in these, regions. I think we've seen adversarial learning. And then this Bayesian one, I have never explored it, but this is uncertainty weighted loss function. Most of these are trying to figure out how can we change the loss function. For Dr. Newsom, the loss function is just tracks a little bit of whether the model is learning or not, it in a more simplified way. And so we've seen trying to say, and I think here one thing that is missing is that, to me, this is the opportunity for diffusion models, because you can condition so many things and you can change so many parameters that you're never going to be able to create that type of data set. And so you can use that as a text, as a hypothesis generation. And so, you see other comments, including text-based explanations generated by large vision models, but this is still very early work. So I thought overall that this was a great paper. I enjoyed reading it. It gave me a lot of thoughts as I prepare for the datathon and what do we want to learn this year. I think it's clear to think about how we compose data sets and figure out the data set distribution. I think we also are challenged to think about metrics and new tasks beyond classification or a binary task classification. The opportunity to apply bias and evaluation, not just in the vision language models, but also in the downstream effect. And this still remains a big a thing that I'm thinking a lot about. How do you think about bias beyond just the classic groups that we have? What does that mean in terms of figuring out about our data sets or how we curate data? And I hope that my explanation at least piqued your curiosity to embrace this challenge, and I'll let Enzo correct anything that I misquoted or yeah. But thanks for attending and listening.
Hi. Well, thank you very much, Judy, I mean, it seems you read it very carefully, and all your insights are amazing. And I think there are many areas that can be improved in the paper. It's actually a book chapter, as you were mentioning. Yeah. We decided to upload it to archives just to make it available early on, because the book is not still available, I think. And also because it's a way to, share knowledge. And this chapter was written, basically, these are the problems that I think are interesting targeting, right? So it's like really subjective somehow. It's what I think it's interesting, and what Rodrigo, the other co-author, and my colleague here in Argentina also think is worth exploring. And you mentioned, I mean, to me, like, discovering biases beyond standard demographic groups, it's something like standard demographic attributes is something that is really interesting, as you were mentioning, and I think it's an open door because to me, standard demographic attributes are sometimes just proxies for the real reason behind the biases, right? And how to discover that, I think it's really a question that we don't have answers. To order a little bit that study, we have continued working on that, also with Veronica Chepligina and her team. And we came out now with a taxonomy of what we think are potential confounders that may give place to biases that we just published in a workshop in MICAI. So I may share then, I think
Yeah,
this...
you should share that, and maybe I'll have you come back and present it, so I don't have to
I
present.
mean, this paper is mostly by one student from Veronica, but we gave her this taxonomy that I've been working with one of my students because we thought it was a nice complement for the paper. So this is the paper, actually. And the taxonomy is just there. We call it MICCAT, Medical Imaging Contextualized Confounder Taxonomy. And I'm sure this taxonomy is missing parts. So it's also open, I guess, to discussion, but it helped us kind of categorize different confounders and how you can, organize them. I think that can help us think about things that go beyond demographic attributes. So the demographic attributes are just one of these branches there, but then you have other ones in the taxonomy.
Yeah, no, thanks for sharing this. This is why this group exists. Now you can come back and do some more reading. And yeah, okay. Questions, comments? I saw some thumbs up from the yes, Leo.
Thanks, Judy. Thanks, Enzo, for that contribution really to the community. One of our big projects, and we would love to recruit other people, is truly identifying the group of people, regardless of their demographics, that are most likely to be harmed by AI. So the name of the project is AI Harms. And I think this would also allow us to move away from the traditional demographics, which we know are not very accurate. And also, they're not even feasible to collect in a lot of places. So rather than looking at fairness across race, ethnicity, or sexual identity, or socioeconomic status, let's try to find more objective labels that we know have better data fidelity. And one of the projects that I think some of you are involved in is let's create 10 models on this cohort of patient. And then we give each patient now a score on how many times did AI get the classification or prediction wrong. So the vast majority of patients will get 9 out of 10, 10 out of 10. And then obviously there will be patients who will get 1 out of 10, 2 out of 10. And rather than optimizing the performance of the model on Black women, those who cannot speak English, let's optimize the model on those patients that we know are most likely to be harmed by AI. And we're doing this for computer vision AI, we're doing this for language model AI, we're doing this for multimodal AI. But that's a summary of 3 or 4 projects that we are involved in, and we would like to do this in every data set. And it's something that we can definitely talk more about in the upcoming Emory event in a month from now.
Less than a month.
Yes, in less than a month. But I think these are different ways of continuing this work without asking the clinicians to ask patients, what is your sexual identity? How much income do you make? Because those, you're putting us at the spot of asking very embarrassing questions. But maybe we create new labels. So one label would be that, do you belong to the group of patients that AI is almost always going to get predictions wrong, diagnosis wrong, treatment recommendations wrong? And then the other project that we have been also looking at is seeing if we could create labels based on the volume of care that people are getting. that is adjusted for all clinical confounding. So some of you are familiar with a project that I think should be in preprint pretty soon, where we look at the distribution of the frequency of mouth care among patients in the ICU, the frequency of turning of patients in the ICU. And although the protocol said that you have to have mouth care every 4 hours, you have to be turned every 2 hours, in reality, that doesn't happen to everyone. And that's another label that we can use rather than, again, depending on race, ethnicity label, or depending on some other label that does not even exist. And it truly covers now all the different axes of discrimination, right? Because we can't really see how the provider is perceiving this patient, because it's typically a combination of how they dress, how they sound, do they look arrogant? And for that reason, this is the decision I'm going to make for this particular patient. So rather that, because we have an infinite space when it comes to why do we discriminate against patients? And there's just no way for us to capture that entirety of how we see, hear, or perceive a particular patient. So I'll pause there and see if there's any gut reaction. We're always constantly recruiting people. And then a huge project of ours is creating a community crowdsourced bias glossary for every data set that is available. So Mimic, we have the fortune of having really tens and thousands of people contributing the data discoveries that they have in the process of doing a project. They found that, oh, we're not collecting blood sugars in the same frequency for people who don't speak English. Or we found that the temporal thermometers are not diagnosing hypothermia and or fever in dark-skinned individuals. So to us, everyone needs to know about all these issues. And unfortunately, most databases, you have no clue about these data issues. We call them data artifacts. We don't want to call them biases anymore, because biases just evoke such negative emotion. But in fact, some people said these are not data artifacts, these are societal artifacts. But everyone needs to know, anyone who's going to use a data set in the future should be familiar with some of the data artifacts that people have discovered in the process of using that data set. So more about that too. We have a paper that hopefully will be accepted soon that talks about this concept of a bias glossary that is community crowdsourced. Over.
Thanks, Leo. Leo is also going to be at the Datathon. Hopefully you'll be feeling a little better. Your voice sounds husky. And I would say, yeah, we flashed out this idea a little more at the critical care medicine datathon about adding these labels. And it's the same, a little bit of what I said. The false positives can tell us a lot. So Pochi and Frank are working on this. I'm looking at Pochi behind me here. So this Emory dataset is going to have these labels for you to start to say, if like a patient can have like 100 labels, right? And then you can start to really see even beyond the binary class, what can you do with that type of work, right? I think it's a really amazing way for us to have discussion. No one wants to build to fight the state of the art methods. We really need to think a bit, how do we actualize something like this? The what else was I gonna say? Other reactions or comments, as I remember my second comment.
Maybe just as a reaction to Leo's comment there on yeah, the projects that look amazing, Leo, what you are commenting on the different projects, but regarding the discovery of groups somehow. So there is a whole literature in the computer, because I've been thinking about that more from a computer vision point of view, that is from where I'm coming, right? So there is a full set of literature on slice discovery. That's the name kind of a thing. That is basically discovering slices, and slices of data are basically data, parts of the data set. For example, I don't know, if you are classifying lions and animals, the lions that are in the sea are misclassified because, of course, there is a background that is a C and it doesn't go with a lion, right? So that's the real reason behind the bias. So discovering these slices of data, in our case, it could be people in hospitalized units which have, I don't know, artifacts like the different tubes and intubation and these kind of things. That could be a slice of data that is discovered as, okay, in these people, we are missing, like the classification quality is lower. So discovering these kind of things is something we can be looking at and thinking about the open vocabulary. Yeah, that's a paper by Ake. So this is the version, the first paper I've seen on slicing in medical. We just have a paper now also that is in ECCB that we are going to present in Milan, that is more computer vision, that is called Big Bias, which goes in the same direction, but in general. So using textual descriptions of images to find the reasons behind biases, to me, is a really interesting topic, like using the VLMs and the open vocabulary of VLMs to say, hey, the system is failing in this set of images. What do these images have in common? Okay, all of them have tubes. Okay, that's the reason maybe behind the bias. So this is a whole direction that we are starting to pursue, and maybe with David, who is here, and a new PhD student who will be starting with us in Paris, we may also explore a little bit of that as well. That's a paper I'm mentioning, yeah.
So there's quite a lot of great nuggets. This is the only way you can prepare for the datathon. Most of these people are coming, so you can talk to them. They're approachable. So just spend some time reviewing some of this work. We have 1 more minute. Any comments? Really? Is it just that when you're in the same room, you're not allowed to laugh loudly?
I have a quick one. So,
Yes.
how would you see like importance to like of getting access to larger and larger collection of data? I know the problem is that data that's available to train are disappearing right now. But for example, like I'm particularly interested in federated learning, right? For example, adding like data collections from different continents, from different, just hospital settings. So intrinsically, we would expect they would reduce bias, right, in certain way. But how do you see, importance of, for example, federated learning?
Let me answer this question for you before Leo lectures us for 1 hour. Federated learning does not result in fair models. I think it just improves access to models. It's a little bit of a myth that you train more diverse models. We did some work around COVID that showed that even just the federated model architecture you choose can be directed more towards generalizability or personalization. But I think I would say still in the gray, which is the big takeaway for this, right? We have to be reading a lot and brainstorming with each other. But I would say that, but other people can react, but I don't know that the assurance of winning
I've seen the work, I think, from Intel that just they showed like increase like of 30% of accuracy on one particular just study on, I think, on brain, like when they use data from, I think, over 80 centers, basically.
Yeah. I think what we know is that you need to have different data sets. So that's why you have to think a lot about the label correlation, right? So because like our Emory data set is very close to Mimic and very different to CheckSpot. And so we never know what data set should I source? And also, if you're trying to build another data set, like why should we release another Emory data set? Like what's missing from the current ones, right? So, one way that I thought is that we had looked at out of distribution techniques, which have been worked on a lot, and said maybe the way to train federated model is to say, here are the out of distribution samples. And so it's also very compute intense. Instead of training again the whole model to teach normal that the model is doing good at, you can show this small subgroup of patients. I haven't seen this before, and I want to work on that subgroup or improve from that subgroup. And so, other people, there are amazing people on this call, but they can comment about it. But I think usually when most people say federated learning, it's just seen as a reassurance that everything is okay, and it's not. Awesome. Thank you, everyone. Hope to see you 23rd, 24th, 25th is the Datathon, the summer school where we'll be discussing sort of like practical lessons of how you should approach machine learning problems is Monday to Thursday. The site is datathon.org. So thank you and have a good 2 weeks ahead. Bye.
Thank you.